And hello, YouTube. So this is a recording for a very interesting package I found. It's called Metrolopy, and it helps you to sort of deal with uncertainty propagation. If you look at Wikipedia, there's actually a list of uncertainty propagation software. So this Metrolopy is one of them on this list. Here it is. It's licensed under GNU GPL. There's a lot of it's a Python library, so should be quite easy to use for if you're already familiar with coding. And yeah, it has a lot of features. It has calculators, libraries, everything. You can even yeah, do a lot of stuff with it. So you can make your own library out of it as well. So what is it based on? It's based on this guide to the expression of uncertainty in measurement, otherwise known as GUM. And this is uh, by the meteorology people. So this organization JCGM, they actually did this GUM guide for uncertainties and everything. So I'm guessing that's why he calls it the creator. The creator might have called it a Metrolopy. Let me just get some things out of the way. Who made this Metrolopy? You can see the GitHub here. NRC. So it's a national research. I think it's Canadian research or something. Okay. So if you take a look at, if you Google Metrolopy, okay. Oops. Metrolopy. Yeah, and you will see this GitHub IO, and that's the main page. You can go to look at some of the tutorials there. So this is by Harold Parks from the National Research Council in Canada. Okay, is this distributing this under GNU GPL3? So any code that is based off this, you will also have to do it under GNU GPL3. Yeah. So we are using it here just to demonstrate some use cases, okay, and how to use it. All right. So I hope you're familiar with uncertainties already. So I won't be going through too much. Okay, but if you spend a lot of time calculating uncertainty, you know how tedious it is, right? So yeah, I just want to introduce you to this Metrolopy because I didn't find many tutorials on YouTube about this. It's a very interesting package. So let us start with let us start with a markdown document. Okay, so this is what I'm doing here, a markdown document, and this is called Basics of Metrolopy. This is like the first example I'm doing in the GitHub. Maybe it's one of a few examples or maybe one or two examples. Okay, so let's say we are trying to find the hydrostatic pressure. So this is a very fluid mechanics thing to do. So I do a lot of fluid mechanics. So okay, delta P equals to delta H rho G, which is the pressure difference equals to the height difference in if you are using manometers to measure, density rho, and G, which is the gravity. Okay, so if you're supposed to find uncertainty of this delta P, you'll need to actually know your uncertainties of delta H, rho, and G, all of these. So if you want to look at the GUM guidelines of uncertainty, what you're supposed to do is, all right, I think I'm missing a bracket here. Yeah, you're supposed to, this is the combined uncertainty of delta H. If you're doing it for delta H, for example, you have to do some partial derivatives based on this what delta H is based on. Yeah, you need to do some partial derivatives on delta H. So delta H equals to H2 minus H1. So you just take partial derivative with respect to H2 and H1, and this is what you will get. Okay, this uncertainty equals to the uncertainty of the uncertainty of delta H equals to uncertainty squared. Oh, okay, this is like variance. Okay, uncertainty square of delta H equals to uncertainty square of H2 times, okay, if your uncertainty is plus minus 1 mm as it is here, then it's just 1 mm here. So I just put 1 here. I was a bit negligent with the units, but you get the idea. So you have the uncertainty. Oh wait, no, it's not pardon me, it's not 1 mm. This one is actually what you get after you do the partial derivatives. So this partial with respect to h2 is just 1, partial with respect to h1 is just -1. So it's the uncertainty of h2 squared times 1 squared plus uncertainty of h1 squared times -1 squared. So the square cancels out the -1, so you don't really need to worry about whether it's plus or minus at the end of the day. Okay, so for rho and g, we do a very similar thing. We need to take partial derivatives and you sum up all the partial derivatives and their uncertainties, that kind of thing, whatever you see here in this expression, and then you just substitute in the uncertainties. So if each manometer reading is 0.001 meters or 1 millimeter, okay, yeah, if each manometer is 0.01 or 0.001 meter or 1 millimeter, then we'll need to sort of add up these uncertainties here to calculate uncertainty of delta H. And then we'll need to factor in the other uncertainties like gravity and also the density. Okay, you can see that the calculation of uncertainty is somewhat very much more tedious than calculating H rho G already. Yeah, so that's why we kind of wanna do code. Okay, let the Python do all this uncertainty calculation for us. Okay, but anyway, we'll just walk through the procedure first. If you don't want this part, you can just skip it ahead. So next, so besides delta H, okay, you have this uncertainty, which is based on H2 and H1 plus minus 1 mm each. There's also the gravitational acceleration uncertainty, which is about 9.81 meters per second squared. So what's the uncertainty? Okay, it depends on what kind of instruments you're using. Okay, so some experiments they have done a measurement of gravitational acceleration by dropping atoms. So this is a very good paper in Nature. You can actually take a look at that, done by very good people in Stanford, almost 20 years plus years ago. So 3 times 10 to the minus 9, very, very low. So it's almost negligible if you want to talk about 3 significant figure kind of thing. Okay, so you can think about it like that. You just reduce that uncertainty to almost 0 for most intents and purposes. Or we can of course find uncertainty another way, or at least deviations another way, by considering that gravity actually varies from place to place. For example, in Peru, that on this summit of this mountain, it has a measured gravitational acceleration of 9.76. So this is and okay, 9.76392. Okay, so this is like very much how do you say? It's like very high altitude, closer to the equator. And then you have one in the Arctic Sea, which has a very high, very much a higher gravitational acceleration, 9.83366. And those are the figures given in this paper. Yeah, 5 decimal places. A root mean square value is about 9.80. So maybe you want to put that kind of variation in, and we find that the variation to one significant figure is about 0.03. So 3 significant figures for gravity is quite reasonable given this variation. You don't consider just this measurement uncertainty, but also this natural variation in gravity. If you want to put that in as your uncertainty, you're more than welcome. So that at least this correlation here actually works throughout the whole world, no matter where you go. Okay, so this actually takes into account the gravitational variation. Okay, so it's 9.80 plus minus 0.03. And so the last part we want to consider is our density first, So for thermal or diatherm, this is a heat transfer oil commonly used I think concentrated solar plants, or at least it was thought to use, it was considered for use in solar concentrated CSP, concentrated solar power plants, or some other experiments as well. Okay, at 20 degrees C, the density is 1061 kg per meter cube. Okay, uncertainty is plus minus 0.5. Okay, this is where you actually can get the thermophysical properties from. This terminal or diatherm is actually just a eutectic mixture of diphenyl ether and biphenyl. So this is from the Journal of Chemical Thermodynamics. Okay, uncertainty is plus minus 0.5 kg per meter cube, or in the original units, 5 times 10 to the minus 4 grams per cm cube. Now, if I made a mistake, at least this original value is there. Okay, but it should be 0.5 kg per meter cube. You just times 1,000, if I'm not wrong. You times 1,000, and you should be able to find the appropriate value. Okay, so to calculate this, we need to sort of sum the square roots up for delta H, 0.00141 meters. Okay, and this expression isn't working for some reason. Hold on, let me quickly correct that. Okay, so here we are. We go through the calculation, substitute all the values. So for one significant figure, the pressure drop, if let's say, still doesn't work. This is very strange to me. Okay, I think now it should work. There you go. Here's the expression. You can go and read it on your own time. Okay, so after substituting in all the values, we will just get around 110 plus minus 20 pascals, 100 or there's one significant figure, 114 plus minus 15 pascals. That's two significant figures if you want your uncertainties to be two significant figures. So you can see that the amount of effort we use to calculate uncertainty of delta P here is quite a lot more than just multiplying all these three values together. So H rho, delta H rho, and G, we need first to find, of course, all the uncertainty values, and then do all these partial derivatives, which, well, we can make mistakes, especially if the formula becomes very complicated, or for very for very long formulas, it can get very hard to keep track of all these uncertainties and propagations. So the very good package to use for this, if you want to do it, is in Python, and it is this Metrolopy code. Now, how do we do this? Well, I'm going to start by introducing you to some of the code I've written here. Okay, I'm using Vim, new Vim now, so you might want to take a look at the bottom right side to see what keys I'm pressing. Okay, but yeah, I'm using NeoVim now, and node monitor. Maybe I'll use vsplit. Yeah, I'm going to run this code and do node monitor on it. Okay, so this I'm running an SSH with node monitor. So, and now of course, yeah, you'll get to see how to use this Metrolopy code. Okay, so first thing first, you want to do is install Metrolopy. Okay, this should work on Windows and Linux. Okay, so for me it already works, so it doesn't really matter. Okay, so what I want to do is, okay, in my repository here, you go to the terminal folder, because this code is supposed to run in terminal. Of course, there's a Jupyter Notebook version, which is what Metrolopy is sort of meant for. It's meant for Jupyter notebooks. So this is the way you can actually take a look at their tutorials. Now, of course, the tutorials do cover the basics. Mine goes a little bit more than that. Like for this situation where we'll start talking about yeah, units and stuff that, you know, the tutorial may not cover. You'll see it shortly. Now, Metrolopy is sort of yes, it's meant for Jupyter Notebook, but I like Vim, so I like to work in terminal. It's very minimalistic, very much faster in terms of code running speed. Yeah, and agronomics for me. Okay, I'm very used to it. Okay, so or at least more used to it than VS Code. Okay, so what I need to do is to do node monitor. Okay, node mon. Or rather go to the terminal, cd terminal. Okay, this is example one. Node mon main.py. Okay, so here is the example. You can actually use node monitor or simply just Python to use. Okay, main.py. All right, but okay, I also want to sort of help make things a little nicer by doing Jupyter Notebook a little bit later. Okay, but let me run you through the code first, right? So the first thing first, how do we use this code? We install Metrolopy as you saw, and then we need to import it. Okay, so in the tutorials we usually use Metrolopy as UC, import Metrolopy as UC. Because UC I think kind of means uncertainty or something. And what we're supposed to do is to make a dummy object right here. You see, for example, if I want the H1 just now, which I was doing for this hydrostatic pressure example, H1 here, all right, H1 over here, it will have a value and a certain uncertainty. So this is H1. So your first argument is maybe a value 1.05 meters, part of a manometer reading, 050, uncertainty 0.001. Okay, then you can put the unit here as meter. Now, what kind of units can you put or don't put or not put? Later we'll find that out. Okay, but for now, just take it that we can add units here. So H2 is a similar thing, and delta H is H2 minus H1. All right, and then what you can do is just print H1, print H2, and delta H. Now I'm going to comment out all these lines here. Okay, I'm going to comment out all these lines, and then I'm going to use nodemon main.py. Okay, so you can see just by doing that, we actually can get the heights of the manometer H1, H2, and delta H here. You can see that the uncertainty here is about 0. Yeah, you can see the uncertainty here. These two numbers actually pertain to the last two decimal places here. So it's 1.05. Or rather, let me use the cursor much better. This is 1.05 right here, 1.050. Okay, these last two decimal points right here, actually, they will have the uncertainty associated with them in these brackets. So again, here for this reading, 1.0610, they have an uncertainty of 110 at the back. Okay, and last but not least, we have the combined value. So we actually sum both of these squares up and take the square root, and then you do the subtraction here, but you add up the uncertainties, or you add up the variances, and you take the square root. Okay, so that's basically how to initiate objects. Okay, next step. Okay, you want to start dealing with acceleration. Okay, and let's start talking a little bit more about units now. Okay. Okay, so all right. I've indented. Okay. Let me print setting up gravity. Yeah. All right, there you go. All right, so for gravity, as you can see, we need to actually put in units. Now, before we talked about units, some are quite obvious. Like for meters, you just put one of those m down there. But for gravity, you have like meters per second square. So if you want to do a unit search, you can use this search units function. Okay, on the Metrolopy, you will see the HTML being put out over here. You see, yeah, units search, unit underscore search, or rather search units. Okay, you see the search units function, you see search units, length, then the format is HTML. So this works very well for Jupyter Notebook. Doesn't work well for terminal here. Okay, doesn't work well for terminal. Okay, so what happens is that if you don't want to use Jupyter Notebook, though likely you might want to, okay, if you don't want to use Jupyter Notebook like me, then you can print it out with UTF-8 and make sure you show all the units. Okay, show all the units, add this argument here, otherwise you won't be seeing very much. Okay, so what you can do is you see all these units here. These units are in Galileo. And you can see the unit for Galileo here is actually 1 centimeter per second square, which is not SI, not very convenient. Okay, but this is, the Galileo is a unit you will see often in literature if you actually look for gravitational acceleration. Okay, so Galileo is being used here. Of course, it's named after, well, Galileo after all. Okay, but yeah, that is the appropriate unit. Okay, but this is not a meter per second square. And what's the closest thing we have here? We can use this thing called Hector Galileo, or HGal. This is 100 Galileos here. The alias here is what you need to key in as your string, HGal. So for that, we can actually make a UC Gummy. Okay, again, the Gummy is because it's named after the Guide to Uncertainty Measurement, or GUM, G-U-M. So I guess the objects are, again, it's not I guess, it's the author wanted the objects to be called gummies. Okay, so that's why. Okay, let's just delete all of this. All right, just to get out all the linting out. So the gravity equals to UC Gummy. Okay, we will use the values that we calculated just now, 9.80, and the uncertainty is 0.03. Units are HGal. So I'm going to print this out. Make sure to check your indents. Okay, and Node Monitor will actually print this out with gravity in SI units. Okay, come on. Yeah, gravity in SI units is 9.800 plus minus 0.0300. Okay, this style is a very short-handed form of doing things. My preference is, yeah, my preference is of course to do it using a plus minus notation. So you can do that by changing the style attribute, or the style attribute on that, or the style, piece of data in there, and then you can print G again. Oops, 40 down. Yeah, you can print G again right here. Yes, you can print G again, and this time you will be given the plus minus 0.030 HGal. Okay, so let me scroll this down so you can see a little better. Okay, HGal, and maybe I should just make the font a bit bigger so you can see a little bit better. Pardon if it's too small just now, but okay, yeah, 9.8 plus minus 0.030 HGal. Alright, so next thing we want to key in is density. Now for density, things are a little bit more difficult because there's no default unit for density. In fact, if you try to search units for density, you will run into errors. Okay. Okay, come on, let's just scroll down. Yeah. You can see that the results you will actually get from the search units. Okay, the results you get for search units, you will just get things like Gauss and Tesla. This is magnetic flux density, not the density that we are interested in. So this is something that the other tutorial, it does not really cover in depth, but well, we can actually do some workarounds for this if you don't want to go deep into code, because I actually searched the source code, and as far as I can find after a quick search, I could not find the density values for like kg per meter cube kind of density, mass density. So I decided to do a little bit of a clunky workaround. Now, I could be wrong. There may be density and I just didn't find it. But this is a workaround you can use in case the units you want don't exist. And these must be compound units, like derived units. So what I'm going to do is first, okay, why not we search for volume and we search for mass and then we combine both of them together. And as it turns out, there are many units for volume. Okay, there are many units for volume, such as a barrel, deciliter, 1 liter equals to 1 dm cube, yeah, megaliter, microliter, so on and so forth. So we are looking for a 1 meter cube kind of one meter cube kind of volume measurement, because we are having a mass in kg, volume in meter cube. So what's the closest thing to meter cube here? Closest thing to meter cube here is 1000 liters or 1 kiloliter. Okay, 1 kiloliter is here. This is actually 1 meter cube. So so we can actually just do this. Okay, we'll make a 1 meter cube unit. Okay, we'll make a 1 meter cube unit right here. 1 meter cube equals to UC gummy. Then we'll just put a 1 down there. Of course, you can put a 0.0 as well. I think you should at least, but for Python, it doesn't really matter so much. For Rust, it does. But anyway, this is Python. Uncertainty, I'll just leave it as 0 first, because the uncertainty, I'll just put it in the numerator, because this is the denominator. So this is 1 meter cube. UC gummy, 1 meter cube, uncertainty is 0, unit is kiloliters. Then next thing we can do is to, okay, add the mass in. Okay, the mass part is the numerator. And we can just key in our density right here, because we are just dividing this fluid mass by 1 meter cube to get the density 1061 divided by 1 kg per meter cube. So our mass density number, the value, we'll just put it here. Uncertainty, we'll put it here. The unit for mass will be kg, because that's in the numerator. Okay, so now we can just print out that density. Again, it's a very clunky way, but need to comment out these lines as well. Okay, my SSH is getting a bit laggy. Okay, let me, yeah, anyway, so yeah, density equals to fluid mass over 1 meter cube. So this is our way of obtaining density, and we can see that our density here is 1061.000 plus minus 50 kg per liter. Okay, so this is what we were keying in just now. This is what we are keying just now of over here, 0.5 kg per meter cube. Actually, yeah, I think my uncertainty was wrong. Let me change this. This should be 0.5 kg per meter cube. Yeah, I think that looks more like it. Okay, so I miscalculated that. Okay, but anyway, it doesn't really change the final answer too much, because this uncertainty, this in density, has such a small contribution. So all you need to do now is to just multiply your gummy units together, or gummy objects together. Okay, so pressure equals to delta H, density, and G. Okay, that's the H rho G. And now you don't really need to worry about doing all those things, all those calculations manually. Gummy will take care of it for you. So if you just print out the pressure drop, you will see that pressure drop is 114 plus minus 15 H gal kg meter per kiloliter. Very awkward unit, but this is something you can like live with. If you can live with it, sure, but for pressure specifically, it still has the pascals unit. Okay, so you can actually change the unit to pascals. We can change the style to plus minus to make it nicer, and then we can actually print pressure as well. Okay, So after we save it, node monitor will run the thing again, and here we are, 114 plus minus 15 pascals. Now if you want a one significant figure kind of a thing, you can as well. There was a way to do that. Now I can't remember where I put it. Okay, but yeah, hold on, I'll be back. Okay, I think this is the property we need to set. Number of significant figures and sig here. Usually it's 2, as you saw just inside our node monitor. Usually it's 2 sig figs, but you can change it, of course, to 1 sig fig if you wanted. So let's change the sig fig pressure dot and sig. Okay, the autocomplete doesn't do anything. Let's change it to 1, and then we'll print the pressure again. Okay, doesn't work. Okay, so, well, one significant figure kind of gives us the same answer again, but let's try 0. Yep, we'll see 1.1 plus E plus 2, so it's 110 pascals. Okay, all right, so yeah, this is actually 2 sig figs if you think about it, but I don't see any uncertainties being placed there. So well, I guess the rounding, maybe you have to do it manually. No, if rounding's a problem, I guess we could still do it manually. Okay, so the way to get it, if I took a look at the docs. So one of the things you must print is x, that is the mean value. The other thing is u, which is the uncertainty. So we print pressure dot x, okay, and then we can of course comment this out. Print pressure dot x, okay, we'll get the 114. All the significant figures are there. We can print pressure dot u. Okay, pressure dot u is over here. All significant figures again printed out. So we can just take these values out and then do our rounding kind of manually. Yeah, we can see that these are raw float values that we can just push back into any other any kind of other Python function we want to use. Right, so the Python library that's useful is the sigfig library. So I guess we'll just be installing that. Feels a little bit bloated, but pip install sigfig. And then I'll import sigfig here. Okay. And pip is slow. I think I just hope the internet's working. But let me just fast forward the thing until it's done. Okay, so that stuff is done. So let's do nodemon main.py. Okay, and then we'll just look at the sigfig documentation here. There's a GitHub IO, which I can just copy and paste just to give some credit as to where I found the information from. Okay, sigfig documentation. So we'll just round it off manually. And what is it? Sigfig round. How many how many is rounded? Then you just use the sigfigs property to, or sigfigs input to do it. So let's do I'll change this to round. Okay, sigfig.round, sigfig.round, pressure with sigfigs equals 3. So 3 sigfigs. I think that's all works. Okay, uncertainty should be rounded to 1 sig fig. Okay, so 10.0. Okay. And maybe I want to increase it just to be conservative. Okay, so I'll just go math.ceiling to like get it to hit 20. So this thing actually I want 2 sig figs, yeah. So 2 sig fig here is a clunky way, but in my opinion this is a smaller problem. You can always do rounding later on, after you get the 2 significant version of the, excuse me, yeah, the 2 significant version of this uncertainty. So to me, small issue, but you know, can be done. So 3 libraries here besides Metrolopy, sig fig and math also quite important if you want to do that rounding part later on programmatically. Okay, I think that's all I have. Hope this was useful. But yeah, just want you to know Metrolopy can do a lot more than this. One of the most interesting features it has is a Monte Carlo uncertainty propagation. That means it can actually test the uncertainties and, you know, plot them out using a Monte Carlo way. In case you have different distributions, like you have normal distribution, the other you have a uniform distribution. And the thing, if you want to bring this even further, let's say you have a NumPy library or some other external library that you want to put in Python, or some really big function you already have, but really you cannot use Gummy with it directly, then you can use this apply numerical functions to Gummy. Okay, go to the bottom, you will see that and apply. Okay, and apply static method is similar to the apply method. What does the apply method do? Okay, what does the apply method do? Yeah, so the apply method actually takes in a custom function. It takes in a custom function and some inputs, and basically gives you an output. Okay, I do not know where is that. Yeah, so this apply static method can be used to apply some arbitrary numerical function to a gummy or several gummies. So this is actually pretty useful. If you don't want to code all your numerical values using Python, you can actually just import some other library from another code, or actually just work exclusively with floats and then still use this gummy functionality to help you calculate uncertainty. So this is pretty useful stuff. So anyway, I'll sign off from here. I'll see you next time.